Hey everyone, on this lesson we will apply the Fisher discriminant analysis dimensionality reduction technique to visualize the separation between the digits depending on their class, which is the number that this digit represents. So on the previous lesson we introduced this dataset, right? It is a dataset with 1,797 images of handwritten digits, and the objective of this practice is to separate this number of images into 10 classes depending on the digit that this image represents. So basically we have here a total of 10 classes from 0 to 9. Right? We will do this on this lesson with the Fisher discriminant analysis dimensionality reduction technique. So we will reduce this high dimensionality that we have. Keep in mind that we saw that we had a total of 64 features, so we have a very high dimensional space, and we will reduce this high dimensionality to a lower dimensional space that we can visualize. So we'll do this with the Fisher discriminant analysis. So here, first of all, let's change the name of this notebook to Fisher discriminant analysis. Here let's add a text window just in here for this new section. So let's add here title 2. So let's add a header of 2 hashtags, and let's just write here the Fisher discriminant analysis, right? So we will do this and we will apply this dimensionality reduction technique for 2 dimensions and 3 dimensions. So we will reduce these 64 features to only 2 components, only 2 features, and also with only 3 components with only 3 features. Okay, so essentially, remember the dimensionality reduction technique. We take all of these columns and we reduce this dimensional space to a lower dimensional space, for instance 2, retaining all the information, right? So the objective here is to retain all the information that the 64 columns have. So when we have 2 columns only, or basically only 3 columns, and we have reduced this dimensional space, we are able to visualize, right? And visualize this separation. So let's start with 2 dimensions. So let's add a text window here for 2 dimensions. Here the first thing that we need to do is to import the library of the scikit-learn to apply Fisher discriminant analysis. So here we just type from the library scikit-learn, and we are going to access the discriminant analysis model. We will import the Fisher discriminant analysis, that is in Python called the linear discriminant analysis. Okay? This linear discriminant analysis is the same as the Fisher discriminant analysis. In fact, they are equivalent. In Python, this is the name of it. So we run this. Very well. So here, let's start doing this. Let's first define the model. We can just type the model to be the linear discriminant analysis method that we just imported, and here we need to specify the number of components. So since this is going to be a 2-dimensional space, we want to have 2 components. So here we just type number of components equal to 2. And so now let's apply this model that we just built, okay, to our data, so to our set of images, right? So let's do here the fitting now. Remember that this set of data of images is the x, and the y has the response variable. Okay, this represents the response variable, which is the answer. Okay, basically, which is the real digit or the real number that this given digit or this given image is representing. So now to fit this model to our data set, we just here type, for instance, x LDA, and here we just type the model. The name of the model is LDA, and we are going to apply here the fit transform method, where the first element, the first argument is the data, so the set of images with the features is the variable x, and then we need to specify the response variable. So what is the response variable? Well, here the response variable has the name of y as well. Okay, so keep in mind this y is the argument name, okay, the argument name, and this second y is the value of this argument. The value of this argument is this y in here. If the name of this y was y data, imagine, then here you need to specify at the right y data. Okay, we work with the same name, so we just here change for y, and also this variable y data, we again have y here. So with this, we are fitting this model. So now we can define our data set that we are interested in to visualize this separation. And now to have here this data set, we need to import the pandas library to work with data frames. So we'll go now to the import of libraries, and here we are going to import the pandas library as PD. Now this library here, pandas, is a software library written for the Python programming language for data manipulation and analysis. Once we have this written, we need to also run again this window. Now the notebook is up to date, and here we just need to and write the method of the pandas library. This method is called data frame. With this, we are building a new data frame. So this data frame will have a total of 3 columns. The first 2 columns are going to be the components, basically this variable. Remember that this method returns 2 columns, 2 components. And the third one is going to be the response variable, basically the column y that we have. This y in here. So let's specify this data frame as an input on a dictionary. So here, first of all, we will have the first component, the first column, which is going to be the first component of the Fisher discriminant analysis. Let's just call it FDA1. And we are going to select all the rows of the column 0 of this data. So here we just select all of the rows. Remember, in Python, when you add 2 points, this represents all of them. So all of the rows of the column 0. Next, here, the second column that we are going to add onto this data frame in pandas is the column Fisher discriminant analysis component 2. And we are going to select all the rows of the column 1. And finally, this last one is going to be the response variable. Let's name this final column to be the class. This is going to be the response variable y. With this, we define the data. And also here, the name of this method in pandas is not data frame with a lowercase on f, but instead a uppercase in the f, right? So with this, we're ready to start plotting this visualization and this separation between the classes using 2 dimensions. So to do this, we will need to import 2 things, one for the general plotting and the other for the scatter plot. So here, first of all, we will need to import from the matplotlib library the pyplot method, or basically the pyplot module. So here we are going to import from the matplotlib library the module pyplot as plt. So this library here, matplotlib, is a comprehensive plotting library for the Python programming language, and this module here, pyplot, is a state-based interface to matplotlib. We will also need to import here the seaborn library, so we just type import seaborn as SNS. Is a Python data visualization library based on matplotlib, and it provides a high-level interface for drawing informative statistical graphics. So let's run again this cell. Now the notebook is up to date, and here we are now ready to plot. First of all, let's create a new figure with the pyplot figure method. So here the method is pyplot figure, and we can also specify the size of this figure. Let's, for instance, choose a size of width 8 and also height. And now we are going to represent the scatter plot with the library of seaborn. So here we just type scatter plot. Scatter plots are used to plot data points in the attempt to show the relationship between variables. If we have 2 axes, we have a 2-dimensional plot. So we show the relationship between 2 columns, between 2 components. If we have 3 axes, we have 3 components, and we show this relationship between these 3 columns, these 3 components. So initially we are using 2 components. So here we need to specify the x-axis. So here the x-axis is going to be first column, Fisher discriminant analysis component 1, right? So here we just type FDA1. The y is going to be the component 2, so here the second column. Now then, in a very important argument now, the hue. What is the separation criteria? Well, we want to separate those points, those data points, depending on their class, right? So here the separation criteria is going to be their class, which is precisely the values of the response variable, right? The digit that they are representing, the real number that they represent. Finally, we specify the data. So here the data name is this one, so it is also data, so we just copy this and we paste. And here at the end we can also specify the palette, that is the method for choosing the colors to use in each different class, each different digit and number. So here we will choose a palette, which is the tab 10. Okay, it provides sufficient saturated colors, easy to visualize. Alright, with this we are ready to now plot this separation and this visualization of the separation between the classes on this two-dimensional space. So let's run this. Very well, as we can see, we can now easily see the separation between the classes. How many classes we have? Well, we have a total of 10 classes, right, for each different digit that we see here. So in essence, we have reduced our dimensional space from 64 dimensions with only 2 dimensions now retaining the most of the information. So we can see here that if we take a value, for instance, from this class in here, 4, and we take another of this class here, 3, okay, they will have different values of these features in here. Their values of these 64 attributes will be different because, as we can see, they are very distant to each other. The same happens with the number 0 and the number 4, or the number 0 and the number 6, and so on. We can also see that some digits, some numbers, do share similarity, okay, some similarity of these 64 features. If we take, for instance, an image that is representing here the class 2, the digit 2, okay, and we analyze the values of the features of the 64 attributes, and we take another of the class 3, this red point here, okay, they will most likely share and have some similarity on these 64 features. This is because they're close to each other, right? With this, we can see this using 2 dimensions, right? This dimensionality reduction. Let's now use 3 components. And so now plot a 3-dimensional plot. So here let's set the text window with the name of 3 dimensions. So now let's start by defining our model. Now the model we define it in the same way as before, but now we are going to use 3 components, right? We'll have here a 3-dimensional plot. We will now reduce all these 64 features that we see here to only 3 components, to only 3 columns. We will now apply the fitting. So here to apply the fitting, we do it in the same way as before. However, now this variable here will have the information of 3 columns. Here we will see 3 columns, okay, instead of only 2. This because before we were using 2 components and now we are using 3 components. Therefore, when defining the data, we write here pandas data frame. We will specify now the name of 3 columns. So here, initially, we'll define this as a dictionary. Initially, the first component is feature discriminant analysis component 1. The value of this column is going to be precisely here, this value of all the rows in the column 0. Then we will specify the second column that will have the values of all the rows for the column 1 of here this XLDA model. The same we do it on the last one, which is the component 3. We'll take the values of all the rows for the column 2 from this returning value of this fitting in here. Finally, we specify the class column as before. Okay, so here the class is going to be the response variable y. In fact, something we did not do before, okay, we can do it now. We can, for instance, show here the first elements of this data here. So if we just type data head, we can see the first 5 elements of this pandas data frame. So if we run, we can see here this is the first column for the feature discriminant analysis component 1. This is the second, the feature discriminant analysis component 2, and this is the class. okay, which is the real digit, the real value that this image is representing. We can also see, since we have lots of instances, we have 1,797. Let's see, for instance, the first 100 instances and samples of this data. And we can see here the first 5, as we can see, represent these digits. Then the number 95 represent the digit 6, the 96 the digit 8. And as we can see in the middle, we have something like these 3 dots. If you don't want this to show and you want to see all of them, you can establish a option in the pandas. So here we just type the pandas library, then we use the set option method. And here the option that we are going to choose is to display max rows. And we are going to set this to be, for instance, 500. Okay, so now when we run this again, we see all of the 100 first elements that we are visualizing in here, right? The 0 is representing the class of the digit 0 and so on. Then the 10, as we can see, it is a cycle process, okay? This is a cycle, and also it is a sequential ordering of the images, right? We keep representing the classes 0, 1 to 9, again 0, 1 to 9. Oh, here we find that this is different, okay? For instance, the 30 is 0, but the 31 is representing the digit 9. So it appears that it is not sick at the end and nothing really cycle at the end, okay? So we begin having a cycle behavior, but at the end, this data set is not cycle. We can have here the identifier anyone, and we can have any ordering of the digits. Again, remember, this class here is nothing more than the response variable y. Okay, remember, this is the y. This is representing the real digit that this image represent. Okay, with the 64 features. The same here. Okay, this image 12. Okay, we have this image. This is the identifier, and this class 2 is representing that. Basically, it is telling us that this image with identifier 12 is representing this digit. If we take this image with identifier 62, this class 3 basically is saying that this image 62 is representing this digit with the 64 features. But here we reduced to only 2 features, so we can visualize it, right? So for now, let's clear this output. And here, when we define this data set, now this new data set, let's run this. And now let's do the same thing. Let's just type data head, for instance, the first 50 ones. We type and we press enter. And as we can see, what happens? Well, now the data set has 3 columns. This is because we have 3 components. We are reducing the 64 features of this image, the total 64 features, to only 3 columns, to only 3 features. Okay, and the idea is the same. We take this image 35, okay, and this class 5 basically is saying that this image with the 64 features is representing the number 5. And here we only have 3 columns that represent the number 5. This is because we are applying a dimensionality reduction. We are reducing from 64 dimensions to have only 3 dimensions now. Very well, now to plot this visualization of the separation of the classes using 3 dimensions, we will use here a new library, so we'll need to import a new library. And this is the Plotly Express library, so here we just type import Plotly Express as px. Plotly is a very complete library in Python, supporting lots of chart types, covering a wide range of statistical, financial, geographic, scientific, and 3-dimensional use cases. We are going to import the XPrel model. The Plotly Express is an easy-to-use, high-level interface to Plotly, which operates on a variety of types of data and produces easy-to-style figures. We are going to import it to represent this 3-dimensional scatter plot. So let's run this, and we update the notebook. Now the notebook is up to date. We come here below, and now let's create a new figure using the Plotly Express. Right, so here, the figure, we use the px, which is the Plotly Express, and we just type here scatter 3D. This will create a 3-dimensional scatter plot. So here, the order of the arguments change in respect to the scatter plot in the Seaborn library. First, here we specify the data set. So here we just type data. Okay, this is the data set that we will work with, this one. Then we specify the x-axis. So here the x-axis is the first component of the Fisher discriminant analysis. So we just type Fisher discriminant analysis component 1. The y is going to be the Fisher discriminant analysis component 2, right? And then finally the axis z is going to have here the third component of the Fisher discriminant analysis. And now here the final argument of this method is the color. So how can we specify the color? Well, the color is going to depend on their class that they belong to. So here the separation criteria is the class. So we want different data points that belong to different classes to have different colors, and those that belong to the same class to have the same color. So here the color is the class. Fair enough. Now to share and to show this figure, we just type here fig show. With this, we are going to show the figure that we just initialized. So let's run this window now. Alright, so now we see here this visualization of the separation between the classes. Basically, we can here visualize the separation of the images depending on the class that they belong to, right? We have here a total of 10 classes that represents these 10 different digits that represent numbers. And we can also see here on the right the different colors of these different classes. So we have here a discrete classification. Here this blue, this very intense blue, is the value 0, the class 0. Then this here intense purple, the class 1, and so on. Finally, the yellow data points are for the class 9, right? All these images of the digits that represent the class 9. In fact, in the Plotly Express, apart from visualizing, you can also see here that if you move the marker to a given data point in the scatter plot, you can see the class that it belongs to. So this yellow correspond to the class 9. These values in here correspond to the class 6, as we can see, right? This very intense yellow is the class 7 here on the bottom, and this in middle yellow is for the class 8. Now, why is this visualization important? Well, this visualization is very, very important because we can see that here, depending on the information of these 64 features, we will have one class or another. Okay, this basically means that if we take an image that belongs to the class 7 and an image that belongs to the class 2, they will have different values of these 64 attributes, of these 64 features. That is why it's important to see this visualization and to visualize this separation of the digit images depending on their class. Okay, and we do this now reducing this 64-dimensional space to only 3 dimensions, so we can visualize it, right? With 3 dimensions we can visualize, and as we can see, these 64 features classify the cluster or the group or the class that the given digit image will belong to. Right, this digit images is for the class 7. Okay, they will have similar values. All of them will have similar values of the 64 features. Then if we here move on the top, we see the class 1. Okay, this is another group, another cluster. So since this is another class, if we take a data point, a digit image in here of this class 1 and another one that belongs to the same class, they also will share similarity of these 64 features. But if we take a digit image, a data point here that belongs to the class 7 and another of the class 4, these 64 attributes will be different depending on this image and on this image, since they belong to different classes. And also the distance is important. There will be classes that will be a bit similar. This means that the 64 features will be a bit similar. Okay, 2 classes that are very close together. Okay, for instance, the class here 8 and the class 1. Okay, they're close, a bit close, but if you take lot distance, classes that are very in a very high distance, then they will not share any similarity at all. But here the most important conclusion is that if we take images, basically digit images of the same class, they will have similar values of these 64 features. And we are visualizing this now with 3 dimensions. With this, we finish this lesson. We remind the student that you can download all of this code and all of this notebook on the downloadable documents of this lesson. I hope you have enjoyed the lessons, and with this practice, now you are already prepared to apply the Fisher discriminant analysis dimensionality reduction technique on Python and understand its visualizations.